Hello everyone. Today I'm going to talk about the divergence theorem. And I'm going to try to give some intuition behind what's going on here. So, what is the divergence theorem? So, you've learned that the divergence theorem is that the surface integral is the flux, or the surface integral of a surface is actually equal to the triple integral of the divergence of the field over the entire volume. So, how does this work exactly and what's going on? Let me try to draw a few vector fields through this sphere and it's going to start to make more sense. So, let's say we have this little spot in the center of the sphere. And it's going to two arrows pointing in and two arrows pointing out. These arrows are of the same length and of the same magnitude. Next, I'm going to have four little arrows pointing into this little cube here. But I'm only going to have two arrows pointing out. So, next, I'm going to move on to the third little cube here. These little cubes are actually the infinitesimally small cube dv. But here I just exaggerated their size for visibility purposes. In this case, I have two arrows pointing in and four arrows pointing out of the cube. Next, in the final example, I have two arrows going in and two arrows going out. But the length or the magnitude of the arrows going into the cube is much longer than the arrows going out of the cube. So, now I talked about this, I can start to discuss divergence. In this case, in the little spot in the center of the cube, let me put a little infinitesimal box around it too. There we go. So, in this case, there are only arrows pointing out of the cube, little cube here. There are no arrows pointing into the cube. That means the divergence at this point is greater than 0. What the divergence tells us is that there's a net flow out of the cube. There's a net flow out of this little infinitesimal cube in the center. In this case, there is an equal number of arrows going in and going out. So there's an equal amount of flow going in and an equal amount of flow going out of the cube. So for this cube, I will say that the divergence, let me make this bigger, that the divergence of the field at this cube is 0. So good so far? In the next example, I'm going to talk about this cube. In this case, there are 4 arrows going in, but only 2 arrows going out. So there's the net flow into the cube is much greater than the net flow out of the cube. That means the divergence of that field here is less than 0. In the fourth case here, there are only 2 arrows going into the cube, but there are 4 arrows going out of the cube. That means the divergence, the net flow into the cube is much less than the net flow out of the cube. So, the divergence of the field here is greater than 0. And for our final example, for this cube here, although there are 2 arrows going in and 2 arrows going out. The strength indicated by the magnitude of the vectors here, the strength of the flow in is much stronger than the strength of the flow out. And so the divergence here is negative. All right. Now, since I already talked about the divergence over several regions in space, why are these two equal? Let me show you an example that can help you provide more intuition behind what's going on. But before I get into that, there's one point I need to mention. In this case, we have different divergence values all over the sphere, but we're doing a triple integral. So what this means is we're going to add up all these little infinitesimal boxes in the sphere, and we're going to add them up. And so we're going to add up the positive ones and the negative ones and the ones that are 0. So when we add all of these values up, we're actually calculating the net flow from this sphere. And so by the net flow from this sphere, after we've done the triple integral, is actually equal to the flux just directly across the surface here. This is actually equal to the net flux across just the surface of the sphere, not the interior of the sphere, but just along the outer layer. And let me proceed to the next example because that will help things make more sense. So, in this example, I'm going to try to have an x, y, and a z axis. So I'm going to have an x here, and a y here, and a z here. And I'm going to draw a really big sphere. So this is our sphere. And I'm going to draw this little box over here. So here's our little box. And the vector field I'm going to make is, I'm going to try to make it simple. So I'm going to have all the arrows equally spaced, and they're going to all have the same length. And they're all going to have the same direction, so they're going to point upward, like this. So it's kind of like a gravitational field, but in the reverse direction, so everything's going upward. Next, I'm going to draw this little shingle over here. And a little shingle over here. A little shingle on top, and a little shingle to the right. So now let me start to draw the arrows through the sphere. We will have 2 blue arrows, just like the black arrows here, that point into the sphere. I just used the blue just to make it a little more clear. Here are the blue arrows pointing out of the sphere here. This little block here is our infinitesimal volume dV. So think of it as a little cube. Next, I'm going to have the vector field point upward out of this shingle. And again, out of this shingle. Here we go. And these are the last 2 arrows. Next, for calculating the flux, remember that we need to talk about the normal vectors of the sphere. So in this case, the black normal vector points down. This is our normal vector, little n. And in this case, because the walls of the sphere start to curve upward, instead of it pointing, in this case it points down. So the normal vector is our black marker, it points down. But as the sphere starts to curve upwards, the normal vector is going to point to the side. So it's going to point to the lower right. In this case, the normal vector points toward the upper right. And in this case, here I'm going to draw here. The normal vector points upward in the same direction as the field vector. So the blue is our field vector F. And the little black arrows are our normal vector N. Now, what do you notice here? We've noticed that because the field is so symmetrical, because the blue field F always points upward, that means it enters the cube in the same direction as the direction that it exits from. And so, we've noticed that the angle here, for this case, they're 180 degrees apart. So the field vector blue points upward and the normal vector points downward. In this case, the angle between the two vectors on top, they're in the same direction. So the angle between them is 0. Next, for this case, I'm going to work on this case first. So, it's alright, I'm going to work on this case. So, this is a little more tricky since it's not at 180 or at 0 degrees. So, you have this normal vector pointing outward, but this vector pointing inward. However, vectors can be moved. So I'm just going to try to draw this as a little dotted line, just to symbolize the movement of the field vector upward. And now we can calculate the angle. So, let me call the angle between these two vectors theta. And in this case, notice how this angle theta and this angle is complementary. In this case, if we draw another little dotted line, the angle here is also theta. And so the angle here, let me call this theta prime, is equal to 180 degrees minus theta. So good so far? All right. The reason why I can say this is due to the symmetry of the vector field F pointing upward. Now, let me try to explain both sides of the divergence theorem here. So, I'm going to actually start by computing this. So, in this case, I'm going to compute the surface integral . Now, the book doesn't use the loop sign, but what the loop sign means is we're basically computing the flux over the entire closed surface. And so the surface is closed. That means, in this case, here's our F dot dA. These little shingles right here, these four cases, this is for computing the flux. In this case, I will use this for the divergence theorem, but the end result will be the same. Let me explain. So here is our surface integral. Unfortunately, when you take an integral, you're taking all infinite elements over the surface. So we're actually having an infinite number of shingles over the surface. However, I'm just going to show these four examples just for simplicity. So let's take the first one. Let's take F dot D. Let me take the dot product. So in this case, I'm going to take the dot product of the vector F and the vector N. And the angle between them is 180 degrees. I'm going to add them up. And this is for the second one. F and N are both in the same direction now, so I put cosine of 0 degrees. Next, I put F times the magnitude of the vector, blue vector F, and the magnitude of N times the cosine of the angle theta between them, plus the fourth one, which I'll use theta prime. And I just added the 3 dots because an integral is technically an infinite sum. And so when we're taking this surface integral here, we're adding up all infinite elements. But I'm just going to show these 4. Next, we know that cosine of 180 degrees generates a minus sign. So here we go. You notice these two are in opposite directions. This has a minus sign and this has a positive sign, just like how the vectors here are 180 and 0 degrees apart. That means these two cancel out. Next, I move on to the third and the fourth ones here. So, here's our cosine of n. But one of the properties of cosine is if you do the cosine of its complementary angle, it also generates a minus sign right here. And so these two cancel out. These two cancel out here. So we still have the cosine of theta, but now we have a minus sign in front. And a minus and a plus will cancel out. So these two cancel out, and we get our final value is 0. I didn't show it for all the other infinite elements, but because the field is symmetrical, you can kind of visualize how this would happen. Next, let's not use the surface integral method. Let's use the divergence theorem. So now we're going to take a triple integral over the volume too. In this case, notice how all the field lines are pointing into the sphere, and all the field lines are pointing out of the sphere here. So for this little block dv, its divergence of f is 0. So this is our first method. This is our second method. In this case, it's actually true for all little blocks dv in this sphere. Because the field is pointing upward, every time that you have a field vector going into the sphere, it will also go out of the sphere. And so if you pick any dv, not just here, but anywhere located along the sphere, the divergence is going to be 0. That means the inner part, our integrand, is going to be 0. So when we integrate 0 all over the sphere, it's still going to be 0. And do you see? We end up with the same answer on both sides here, but using the second method, it's much faster than the first one. If you do problems in the textbook, when we actually have to do the actual math, sometimes your vector field can be very complicated. But because you're taking the divergence here, what you're doing is you're actually taking the derivative. When you take those partial derivatives, sometimes a lot of the unnecessary variables can go away. And so when you integrate it over the volume, you actually get a much faster answer. Let me bring up one last key point here. And that is the divergence theorem only applies for closed surfaces. Let me explain. All right, good. We're still good on time. So, let me give you this example. Let's say we have half a sphere. So if we, this marker's running dry. All right. Let me just use the blue one instead. So let's say we have this hemisphere here. So we have half a sphere. And our vector field, again, is going to be a simple one. They're all going to be pointing in the same direction upward with the same magnitude. So we have the same length of the vectors. The final set of arrows are actually going to be kissing or touching the top of the sphere. So that's why I have these little shingles. Next, I'm going to have the vectors pointing downward. So again, they're the same length and magnitude as the upward portion, but now they're pointing in the opposite direction downward. I'm just going to draw the normal vectors here. And this is our final normal vector, so it points to the left. In our bottom example, we have a disk at the bottom. So we have a hemisphere at the top and a disk closing the bottom of this hemisphere. And for the bottom, the normal vectors all point downward. So this is our setup right here. For this vector field, let's use the divergence theorem. We notice that the divergence here, everywhere along the solid, is 0, except for this portion. So in this case, for this case, we have the same number of flow in as the flow outward. So we don't have any divergence. The divergence here is 0. In this case, the divergence here is greater than 0. In fact, it's even greater than our last example, because between this versus this, in this case, you only have flow out in one direction, but in this case, you have flow out in both directions. So the divergence of this is actually going to be greater than the divergence of this. Now, let's try to create a counterexample and let's test to see if we can use the divergence theorem for an open surface. So let's say we remove the disk at the bottom here. Now, using the divergence theorem, we have divergence just along this line. And so we have our flux up at the top of the surface. But when we take a look at the bottom, the divergence of this is clearly greater than this. So we not only have to look at the top, but we have to look at the bottom portion as well. And so there is a net flow downward as well. But we don't have a disk at the bottom. So we don't have all these little shingles here to take the surface integral of. Let me just cross them out here. And so what's going to happen is our triple integral over the volume dv. So here's our surface integral. Its value is actually going to be much greater than the surface integral. Its value is going to be much greater here because we assumed, or in our problem, we don't have a disk at the bottom. So there's no flux to be calculated along the bottom. But the divergence here is not this. When you take the divergence of the vector field, since it's pointing both up and down, we're looking at this. This value of this divergence is greater than this. And so your value is incorrect. You would actually get a much larger value if you use the divergence theorem than what you're actually supposed to get. So I hope this was helpful in clarifying the divergence theorem. I know this is the final section of Math 1D, so study hard. During the next section, I might bring in a few physics examples for just a few videos on the divergence theorem in order to help make it make even more sense. Good luck, guys.